Okay, let's come back to the last hour of our class. So basically for the past lecture and this lecture, we talk about complexity theory. So in general, the name of our course is called Algorithm Analysis and Complexity Theory. But typically for a course like this, we talk significantly more about algorithms. And there can be, like a separate course on complexity theory. I think there is a Chinese version of the complexity, a graduate level complexity theory course offered this semester. But actually, for this class, we are actually going to have two lectures. For the rest hour, we will actually contain a little bit more advanced complexity theory knowledge. And if you're interested, you can feel free to further learn into that. I guess for this course, I guess in general, I guess the NP-Completeness part is probably the most important because this really contains algorithmic ideas, and also on the other hand, it tells you what kind of problems are probably difficult. Probably maybe if you maybe encounter some of the NP-complete problem here, you will probably not expect to find a polynomial time algorithm for that. And if you find that, I believe you just show a p equals to NP, you're probably going to be even say like a Turing award. So that is just going to be fantastic. But that is probably going to be too ideal to be true. So this is probably going to help you understand, on the one hand, what is like a reductions. Algorithmic ideas can be in complexity theory. And of course, on the other hand, it's going to let you know that what kind of problem is probably just going to be difficult and probably not going to be expect to find a polynomial time algorithm for that. Okay, nevertheless, for this last hour, let's talk a little bit more about complexity theory. So let's say this part is going to be called more complexity classes. So of course, complexity theory itself can be like one separate course, and there are really deep materials inside that. So we will say that we only talk about like a sketch of more complexity classes. So far, so we have actually defined a P, NP, actually a co-NP, and actually exponential time. So there are actually some other complexity classes. So let's actually introduce some of them. So in particular, there is another very important complexity class called P-space. So P-space is basically the complexity class for decision problems, basically solvable in polynomial space. So a main theorem for the P-space is that actually NP is a subset of P-space. So let's actually prove this. So the proof is actually not so difficult. So actually for a proof, let's just consider an arbitrary problem. Y is in NP. So since we know that actually Y can be polynomial time reduced to the three-set problem. So basically there exists an algorithm that solves Y in polytime plus polycos, or formally polynomial cos, to the three-set black box. But actually, for the three-set problem, the space complexity is actually quite straightforward. So it only has n variables. We just test all of them, so can be implemented in ON space. And we just by brute forcely check all the possible solutions. For n variables. Question. So in practice, it's just like, we have Boolean variables. So we have Boolean variables like x1, x2, until xn. I mean, the space complexity is just O of n here. You just like test 0, 0, 0. If this is a solution, you just return. If this is not a solution, you just erase the last 0 and have like a 1 here and test whether this is a solution or not. You just, if this is a solution, you just like return this. And if not, you just like have 1, 0, etc. So this is definitely very time consuming. It takes exponential time. But actually the space complexity is just linear. And actually, this is a very good thing for the three set, and especially clearly, you can clearly see that for this three set problem, you can only use linear space. Or in general, I mean, for like an arbitrary problem y in NP here, I mean, because we can run y in polytime plus like polynomial calls to the three set black box, the overall space complexity for this algorithm is only also going to be at most polynomial here. So this is actually just a proof that NP is a subspace of, it is actually a subset of the P space complexity class. So any question on this? So I think this is actually something relatively straightforward. And I think on the other hand, furthermore, can prove that actually P space is a subset of the exponential time complexity class. So this is actually also not hard to prove, but a formal proof requires the theory of Turing machines. So I guess I'm not having like a separate course on complexity theory, because like introducing what Turing machines are, I guess these definitions will just take 1 or 2 lectures. So I guess this is not so necessary for us. But the intuition is just that if you only have a Pauli-sized space, I mean, running exponential time, I mean, if you only have this large of space and you have like all these zeros once, and you're running exponential time, you will actually repeat the same status. Because it's just like 0 and 1 are binary strings of Pauli length. And if you just run exponential time, some of them are just going to be equal. So this is going to say that the problem should have been decided in exponential time, or it will loop forever. And because we are talking about decision problems and tell you whether like a decision and tell you whether this is yes or no. So basically in exponential time, this should actually tell you whether the answer is yes or no. And if you actually see such kind of cycles, and basically, I mean, it's just like all the 0 and 1 strings represents the status of your algorithm and the tapes here. So basically it just means that you will just loop forever and you will actually not solve the decision problem. But this, I have to say, this is just like a very hand-wavy discussion, and like a formal proof of this requires and actually a formal definition of all the complexity class requires the definition of a Turing machine. But I guess this is probably not I'm going to give here. But you can probably see the intuition that the P space is actually a subset of exponential time. So that is going to just say that NP is actually a subspace of, sorry, is a subset of P space, and P space is actually a subset of exponential time. So this is just some quick argument. So something further, I mean, in general, you can probably see that NP talks about the algorithm where you have like a polynomial time certificate. And in general, I mean, the way that, I mean, here, the argument that we show that NP is actually a subset of the P space complexity class. I should say this is really, I mean, this is really like a wild argument that in general, I mean, we just like brute forcefully track all of the strings that we can use here. We just make a direct reduction to the three set problem. So maybe a very natural question to ask is there, I mean, from a complexity theoretic perspective, is there anything between, basically we want to find anything between NP and P space? So this is actually a very natural question that people have been wondering about, and there are actually important complexity classes that actually that is actually between NP and P space, such as one that actually I'm going to introduce in a minute. So recall the definition of NP. is basically by something like this. So formally speaking, we say that actually S belongs to X is equivalent to the case where there exists a polynomial sized verifier T such that AST goes to 1. So the A here is a polynomial time algorithm. And actually, we say that it's just like there exists a succinct certificate for yes instance. So basically, this is the definition for NP here. So we also have been discussing about the complexity class of co-NP. Excuse me, X in co-NP is the case where X not belong to X as equivalent to there exists a T such that actually AST equals to 0. Or equivalently, we say that actually there exists a succinct disqualifier for no instance. So this is the definition for a co-NP here. And maybe, I mean, this is probably a little bit, I mean, the definition of co-NP, I mean, it's probably looking a little bit different from the NP here. So we can actually, I mean, from a logical point of perspective, we can think about like an equivalent definition of co-NP here. So in particular, we know that actually this is equivalent to what? To actually S belongs to X, which is equivalent to arbitrary T with poly length AST equals to 1. So this is simply another way. I mean, if S be not in X, if and only if there exists a T such that the algorithm gives us value 0. It's just like for X is in X, if and only if there for arbitrary T of poly length, the value of AST is going to be 1 here. So this is just another way to say another definition of a co-NP problem. So I guess here, I mean, probably the connection between an NP problem and a co-NP problem is probably a little bit more clear. The only difference, I mean, you look at these two lines. The only difference is the quantifier here, where in NP we have exist, and for co-NP we have an arbitrary here. So we say that it is that the key difference between NP and co-NP is the quantifier for any and there exist. Okay, so a generalization, I mean, basically a generalization between NP and P space is that we're actually going to play with all these kind of quantifiers. So in particular, I mean, we are going to consider a case where you have multiple of them. So a natural generalization. NP and co-NP. It's basically the case where we have multiple quantifiers. Okay, so in particular, what we do here. So we have this kind of complexity classes. So definition. So for every integer I is at least a 1, basically we say that a problem, a problem X is in we say it's in sigma IP. If there exists a polytime algorithm A and a polynomial P such that. So basically, we are going to follow a similar sense of the definition of NP and co-NP here. But actually, we are going to see something like this. So such that actually S belongs to X is equivalent to there exists a T1 in 0, 1 PS for any T2. Yes, etc. So for quantifier QI, TI, 1 PS, A as T1 until TI equals to 1, where we say that the QI denotes, we just alternate between exists and any. So here QI denotes for any or there exists depending on whether I is even. If I is even here, basically we are going to start with for any. And if I is odd, here, exists, any exists, and exists, for the third time, for the fifth time, etc., it is going to be exist. So this is actually the definition of sigma IP here. So maybe you will have a question. Why do we have to alternate between there exists and for any? It's just because, if you have like exist for any, if there exists, for instance, like there exists like a T3 in P, sorry, a T3 in like 0, 1 to the PS. And you have another for any T4 in 0, 1 to the PS. You just merge them together, just like this, like T3, T4 in, 0, 1, 2 PS. At the beginning, you can feel free to choose this polynomial by a two factor here. So this is not a big problem. So as long as you have consecutive quantifiers, consecutive like this or consecutive and, you just merge them together. So you can just feel free to assume that maybe in this definition of complexity classes, you alternate between there exists and for any. And of course, there's no reason to only consider like the complexity classes where we only begin with there exists. We can also feel free to consider the complexity classes where we begin with for any. So I guess for saving our time, let me just copy this here. So here, the new definition is going to be here is going to replace by pi IP here, and all these parts is going to be for any there exist. And here, I guess we have switch the order of the for there exist for any and there exists. So it is actually in this case it's going to be something like this. And after having all these kind of definitions, I guess basically you can see that for this kind of definition, it depends on how many quantifiers you actually have here. So actually, one thing that basically we can notice is that basically this complexity class, it also depends on the choice of the I here. So basically for different I's here, basically for the length of the quantifiers here, it is actually going to influence the size of the complexity class. But nevertheless, we can have a definition called a polynomial hierarchy. So the polynomial hierarchy is actually the set. It is typically denoted as PH, which is actually denoted by the union of all the sigma IP here. So a next question maybe you want to ask is that why I do not define this as the union of all the pi IP here. So the point is that this is basically actually the same. So a remark that we can clearly see is that actually sigma 1p here equals to NP. Pi 1p here equals to co-NP. And actually for the second point, for any I at least one, we know that actually pi IP equals to co sigma IP. And actually pi IP is a subset of sigma I plus 1p. And actually sigma IP is actually a subset of the pi I plus 1p here. So basically we say that this suggests that actually a pH equals to the union of sigma IP also equals to the union of all the pi IP in here. And in particular, we also have this kind of chain, this kind of containment. So actually it is called a polynomial hierarchy to have a reason because it actually has a hierarchy structure. So why do I say that? So at the beginning, you can have this sigma 1p here. This is just equals to NP. And you also have a co-NP, which is actually just pi 1p at the beginning. So you will actually have pi 2p, pi 3p. Sigma 2p, sigma 3p, and I have a pi 2p, pi 3p, etc. etc. And we have this kind of arrows. And actually, we have this kind of have an arrow from A to B. It just means is a subset of me. Okay, so this is just a very basic truth of the polynomial hierarchy. So about all these remarks, so I guess for the first remark, I guess this is just straightforward because this is the definition of the polynomial hierarchy, the definition of sigma 1p and pi 1p here. We just like follow naturally. This is like a way, as we just discussed, this is like a way that we want to further improve the definition of NP and co-NP. So it makes a lot of sense at a very basic case. Actually, they can recall the corresponding definitions of NP and co-NP respectively. So furthermore, we basically see, because of this kind of, like co-structure between NP and co-NP. So we clearly see that actually also on the other hand, pi IP equals to co sigma IP here. So this also follow naturally. So for this part, pi IP is a subset of sigma I plus 1p here, and similarly, sigma IP is a subset of pi I plus 1p here. Is that you just like consider how you actually are going to define the complexity class. Up to here, here we are actually talking about the complexity class in sigma IP here. But actually up to here, you can just assume that the T1 here is an empty string. If you have a T1 here to be an empty string here, and for the other part, for any T2, is T3, etc., it just reduces to pi I minus 1p here. And similarly for this part, it's just like for this part, if the T1 here is the empty string, it just becomes the case where it is the sigma I minus 1p problem. So that is actually the reason why we just feel it's very straightforward to know that actually pi IP is a subset of sigma I plus 1p, and actually sigma IP is actually a subset of pi plus 1p here. And actually we have this kind of hierarchical structure of this polynomial hierarchy, the pH complexity class here. So any question about the definition of pH and basically on this basic remarks? Okay, so we have been talking about, from like a complexity theoretic perspective, we want to find something that is actually between NP and P space. So basically the next thing that we want to prove. The next thing that we want to prove here is that actually NP is indeed a subset of pH. And so co-NP is a subset of pH. And actually pH is a subset of P space. So let's give a proof for this. So I guess the first two things, they are just very straightforward, where NP equals to sigma 1p is actually a subset of pH. And co-NP equals to pi 1p. So let's say that it is actually a subset of sigma 2p is actually a subset of pH. So regarding pH is a subset of p space. This is because for all T1, T2, and Ti for fixed I, they have a polynomial length. And basically, I mean, as the case where we prove NP is a subset of P space, we just basically brute forcefully check all the strings. So we just we can brute forcefully all cases in polynomial space. And this finishes the proof. Okay, so this pH is indeed something that we want. It is actually indeed something that is between NP and a P space. So we also want to further understand, I mean, basically as we have seen that for the last lecture and for this lecture, we have been focusing so much on NP-complete problems. So a very natural question is actually to ask whether there exists a complete problem for the pH complexity class. So this is actually a little bit surprising that actually many people believe that there is no complete problem for the pH complexity class. So let's say that actually for the we actually make a question here. So like what is the hardest problem in pH? So a theorem that actually we make here is that actually this is the reason why many people believe that it does not exist a complete problem for pH. That actually suppose that there exists. So suppose that there exists a problem X that is a pH complete. That is to say, y can be a polynomial time reduced to x for any y in pH. So then, actually, there exists an I such that pH equals to sigma IP. So actually, this just means that basically the polynomial hierarchy, it will not go forever. So basically, this is in this kind of case, I mean, for the case where pH equals to one of the levels, this is actually called as polynomial hierarchy collapse. And also, this is typically, I mean, collapses sounds a little bit too general. And typically, you can make this a little bit more precise to, we say that collapses to its ith level. This is like a precise definition here. So in general, I mean, probably a common consensus, although people don't know how to prove, is that P does not equal to NP. And also another common consensus in complexity theory is that pH probably does not collapse to its some level of pH that does not collapse. But this is just like a consensus of complexity theorists. So as the problem of whether P equals to NP, so the collapses of pH, the complexity class pH is also a known question. It's like one of the most important questions in terms of complexity theory. But nevertheless, I think we can prove this. And actually, I mean, basically, as the theorem states, I mean, if there exists a pH complete problem, this just means the polynomial hierarchy is going to collapse, which is highly unlikely. I mean, according to complexity theorists. But nevertheless, I guess I mean having this is probably going to give you a good understanding that I mean not all complexity classes you are able to find a probably not all for all not for all complexity classes you're able to find a complete problem. So this is a specific case, and actually we can make a proof here. So why is this the case? So since X is an element of pH, which is actually the union of all these sets. So there is going to, it's just according to the definition of set unions. So there exists an I such that X is actually a subset of sigma IP here. So since X is pH complete for any Y in pH, we know Y can be polynomial time reduced to X. This is just going to imply that Y is actually belongs to sigma IP here. So this is actually going to imply that pH, I mean, because Y is an arbitrarily chosen a problem from pH. So this is going to imply that pH is a subset of sigma IP here. But on the other hand, of course, sigma IP is a subset of pH. So therefore, a pH just equals to sigma IP. And this is the reason why probably, I mean, because it's just like, I mean, you have a pH complete problem. It must be at a certain level. And after having you choose this problem, the polynomial hierarchy is just going to collapse at this level here. Okay, so is there any question about this? Okay, so we just discussed that probably there is a consensus that maybe the polynomial hierarchy does not collapse. I mean, but this actually, I mean, we also have, I mean, the first consensus that we have been talking about is that probably P does not equal to NP, although people don't know how to prove this. So actually, the impact, I mean, we do want to talk about, I mean, like the relationship between different, I mean, different feelings, different conjectures. So in particular, maybe you want to have a question about what is the impact by P equals to NP or not. So in particular, we have a theorem saying that actually if P equals to NP, then actually even more P equals to pH. So if P equals to NP, actually P equals to something that is even much stronger than NP here because you have so many quantifiers. I mean, you can actually apply here. So this is really something stronger. So we say that it just means that actually pH basically collapses to the polynomial hierarchy just even collapses to P. So this kind of, you can clearly see that basically the discussion about like P, whether P equals to NP is actually even stronger than whether actually there exists a pH complete problem. Because if you have a pH complete problem, you will know that the polynomial hierarchy is going to collapse at one of the levels of the polynomial hierarchy. But if P equals to NP, it even collapses to the 0th level. So basically pH just equals to P. Okay, so let's actually give a proof on this. So proof, assuming P equals to NP. And basically we want to prove that P equals to pH. So what we only have to do is that we basically prove by induction that for any I, we have that sigma IP and pi IP is actually a subset of P. So assuming that P equals to NP, this is actually true. For I equals to 1, since under our assumption, we know that actually P equals to NP. And actually, or maybe let me write like this. So actually NP equals to P equals to co P equals to co NP. So this just means that P equals to NP and P also equals to co NP. So this is basically based on the assumption that P equals to NP. We know that the first level of the polynomial hierarchy is actually a subset of P here. So now let's continue our induction here. So now, assume the correctness for I minus 1, and let's prove it for I. So basically, let's actually choose like an arbitrary problem X, which is an element of us sigma IP here. So by definition, we know that actually there is a polytime algorithm A and a polynomial P such that actually we have S belongs to X. So we are talking about an arbitrary problem, I mean X in sigma IP here. So basically we are just going to copy the definition of the sigma IP here. So in this case, we know that S belongs to X if and only if exists T1 of length P of S for any T2 of length P of S. So for any QI TI belongs to 0, 1. Yes. As I made a little bit typo here, so and we have a P here. Sorry. Yes. And then we have this A T1 to TI. So this is just the definition of sigma IP here. So how about we consider another problem? So we define the problem X prime as follows. So basically for this problem X prime, we consider this. So it's actually a problem with two strings. So actually ST1 belongs to X prime if and only if we just like copy the rest part. QITI belongs to run to the P of S. T1. So we just consider another problem called X prime, but actually X prime has two strings as the input here. So here, basically, I mean, according to this kind of definition, the thing that we know is that basically S belongs to X. Oh, let me actually reopen this. Yes, actually. Okay. Okay, so in this case, based on this definition, we clearly see that actually S belongs to X, which is equivalent to there exists a T1 of the such that actually S T1 belongs to X prime. So let's call this as X star here. So on the other hand, let's take a look at what actually here, I mean, this formula. So what is actually this is? So this is actually exactly the definition of pi I minus 1 P here. So we say that actually clearly X prime belongs to pi I minus 1 P here. So basically by our induction assumption, we know that actually X prime is actually an element of X, an element of pi I minus 1 P, which is actually a subset of P here. So actually this just means that there is a polytime algorithm A prime such that actually ST1 is in X prime if and only if A prime is T1, because this is the whole input here. And we say that this algorithm is a polytime algorithm. It's actually in P here. So actually, if and only if A prime with ST1 actually equals to 1. So basically putting this into the star here. So basically what we get is that actually S in X is equivalent to there exists a T1 at A prime S T1 equals 2. So what is this? This is simply the definition of NP. So therefore, we know that actually the X, the problem we consider is actually element of NP. But actually by our assumption, we know that NP equals to P. So since we take any X in sigma IP here, we know that actually sigma IP is a subset of P. So similarly, we can prove that actually pi IP is a subset of P. And basically this finishes the whole induction step. And basically due to the induction, we know that pH is a subset of P. And P is a subset of pH, and of course P is going to be pH. Okay, so is there any question about this proof that if P equals to NP, we can further prove that P equals to pH? Okay, so the last thing that I'm going to introduce today is that I'm going to discuss about like a difficult problem in P space. So basically, this is pretty much about pH. I guess for the rest 10 minutes or so, let's briefly discuss about the P space complexity class. Okay, so in particular, I think an important point about pH, basically a pH definition requires that actually the I here. So basically the number of quantifiers on the I here is actually a constant independent of the problem instance. So for instance, it is not a polynomial that grows in terms of n, where n is the length of the input. So here, for the definition of pH, I is always a constant independent of the problem instance. So this is actually critical because we are going to see a more difficult problem. So for instance, what if it does? So this gives a relatively close problem. I guess, I mean, you can clearly see this is a direct generalization from pH. So this is a problem called quantified satisfiability. So satisfiability is just a set. So formally, this is typically called a Q-set problem. A Q-set problem consider the following. So basically, let's say that we have a Boolean formula like x1 until xn. So this is actually a Boolean CNF formula. So we also have this kind of clauses where each clause is like a or of a few different literals, and in general, we for the clauses together we want to end them. So the question that we want to ask is that is there basically such kind of arrangement such that is actually the following propositional formula true. So basically, we want to have this kind of there exists as 1 for nx2 until qnxn. So in other words, it is basically like the definition of pH, but the length of quantifiers is linear in terms of n. So basically like that. So basically this Qn similarly is a quantifier and actually denotes for any or there exist, depending on whether n is even. So if n is even, so there exists x2, there exists x4. So for n is even, it is there exists, and for n is odd, it is for n is even, it is for any, and for n is odd, it is there exist. Or we say this is even or odd, respectively. So this is the definition of QSAT. So you can see that this is like a general, I think from my perspective, this is like a natural generalization from the pH. Basically, we have multiple quantifiers, and also from the SAT problem along this kind of line. So in particular, there is a theorem. So one thing that you can clearly notice is that the QSAT problem is actually in P space. The reason is just similar to all the other reasons that we have been talking about. The problems are in P space. We just recursively try all the possibilities in polynomial space. However, on the other hand, we can prove that actually QSAT is P space complete. That basically for an arbitrarily P space problem, you can make a reduction to the QSAT problem. So basically the QSAT problem is P space complete. So if you're interested, this is actually covered in the Kleinberg-Tadeusz book. So its proof is given in chapter 9.5 of the Kleinberg-Tadeusz book. So a direct consequence for that is basically, I mean, the P-space class has a natural complete problem. So a consequence is that the pH is probably not equals to P-space unless the polynomial hierarchy collapse. Okay, so this is in general, I mean, people thoughts about like the complexity classes. I mean, in general, I mean, people don't even know how to prove whether P equals to NP or not. But people are in general guessing that P is not equals to NP, NP is not equals to pH, and pH is not equal to P space. So this is like a very general feeling about that people know here. So I have, I have 2 minutes. So as a summary, I'm basically going to draw a picture here, and then we finish the class today. So as a summary, let's basically use like a figure to represent the relationship between complexity classes. So we have a P in the middle. So NP here is basically like something like this, and co-NP is more like doing this in the other direction, like co-NP. So we then have the complexity class pH. Oops. pH. And we then have the complexity class P space. And among all of them, the larger complexity class that we mentioned in this class is exponential time. So basically, this is the last figure, I think, in the complexity theory part that I would like to mention is basically about like the relationship between different complexity classes. So I think for the lecture, I mean, for today's lecture, I think basically you need to have a good understanding about the Cook-Levin theorem, and I think basically about the proof of NP-completeness of the problems. And I think in the final exam, we are definitely going to have a problem where you're going to prove basically similar to the style of some problems in homework 5 that a certain problem is actually NP-complete by showing that the problem is in NP, and actually you can make a reduction from like an NP-complete problem to this problem. So we are definitely going to have a problem on this. So for the last hour that we talk about like further complexity classes, like especially polynomial hierarchy. So how we move from the definition of NP and co-NP to polynomial hierarchy, and then like to P-space, the Q-set problem, and P-space completeness. So this is not directly required in the final exam. But I think I think if you only want to like digest like maybe like one sentence or like one figure for the complexity theory, basically for the last hour about like further complexity theory classes, remember this figure. I think it is very important you understand like what is the relationship between the different complexity classes. Okay, so as just I mentioned, so basically as I mentioned at the beginning of this class, so next class, which is going to be the final lecture, we are going to cover approximation algorithms. So we have been talking about NP completeness, and we know that in general, a lot of problems they are just so difficult to solve. But maybe I mean we are okay with tolerate a little bit. I mean accuracy that we can find some approximation algorithm. Then a lot of problem again we can get polynomial time algorithm for that. So I guess this after having taught the complexity theory part, maybe we have a better understanding about like approximation algorithm in practice. I mean in the practical usage of algorithm, actually a lot of places they're actually approximation algorithms. And of course, we will give like a brief summary of the semester. Okay, so is there any last questions? Okay, so if there is no question, so thank you for your attendance and see you next week.